Hello everyone, my name is Kamal and I welcome you all to my YouTube channel. Please comment, like, share and subscribe. So let's start. Today we'll discuss this problem in this video. So the complex, you have an iron complex where you have a CP ligand and carbonyl ligand, and they're asking how many metal-metal bonds are there in the complex. So the important point to note for answering this question is that whenever you have this CO ligand or strong field ligand. So this complex is shown to follow the 18 electron rule. So it's not necessary that every compound will follow 18 electron rule, but in most of the cases wherever you have a carbonyl group or strong field ligand, it is shown that they follow the 18 electron rule. Okay, now if it is followed, there is no problem. We don't have to include any metal-metal bond. If the number of electron is less, then we need to include the metal-metal bond. So let us see how many number of electron it has. Now this is the actual structure which I have taken from the book, and let us see, but without looking at the structure also we can calculate the number of electron it will give to the framework. So there are 2 irons are there, and it will contribute total 2 into 8, 16 electron, and this is a CP ligand, and the CP ligand is coordinating in the form of eta 5. So it will contribute 5 electron each. So total I have a 10 electron. Then there are 4 carbonyls. Carbonyls provide 2 electrons. So total I have 8 electrons. And if you count the number of electron now, you have 16 plus 10, 26 plus 8, 34. So that means if you consider there are 2 iron centers, so you can see there is 2 is there. So it should have 18 into 8, 18 into 2, 36. The number of electrons should be 36. But if I do not include any metal-metal bond, the number of electrons comes out to be 34. So I need 2 more electron, and this and to add 2 more electron, I need to include 1 metal-metal bond. Okay. So that means if I include 1 metal-metal bond, it will provide 2 electrons, and the total I'll get 36. And the number of electrons for each iron will be 18. Okay. So by following 18 electron rule, what we found, this compound contain 1 metal-metal bond, and this is the experimental crystal structure. So you can see there exists a metal-metal bond. Okay. So only 1 metal-metal bond is present in this complex. Okay, let me introduce some more important thing about this. What is the color of this compound? This color is red purple solid. You will get it has a very high melting point, like 194 degrees centigrade. And this is very interesting. Most of the organometallic compounds where you have a metal carbon bonds are not stable. But this compound is air stable. Nothing will happen in air. And when you take NMR, you see some other important behavior also. If you take NMR at a very high temperature, like room temperature, you will get only 1 single peak. Okay, but when you go down at a very low temperature, you start to see 2 signals, one for this kind of this compound and another for this kind of compound. And there are many experimental evidences are also there. So this behavior is known as fluxonal behavior. That means this molecule, these 2 ligands undergoing exchange. Okay. And the carbonyl, there are 2 different types of carbonyls are there. These 2 are known as your terminal carbonyl, and this is known as bridging carbonyl. Okay. So finally, I will tell that the metal has this complex has a 1 metal-metal bond, and to satisfy the 18 electron rule. So 18 electron rule is the most fundamental key for this for solving this problem. Okay, now let us look at another problem. This is very simple. They have given a copper complex with a hexa ammonia complex. Now they're asking that all the bonds are equal or not. If you see, usually when all the bonds are same, when you have a same ligand, the bond should be same. But there is problem is that there is something called John Taylor distortion is exists whenever you have unequal filling in the EG orbitals. Usually T2G, if you have a unequal filling in the T2G orbital also, there will also be John Taylor distortion, but the amount is significantly smaller. But whenever you have unequal filling in EG orbitals, the distortion is significant, and you can see experimentally that axial bonds are slightly longer than the equatorial bonds. So this red color bonds are your axial bonds, and this blue color bonds are your equatorial bond. Okay, so in this compound, the axial bonds are slightly longer than the equatorial bond, and this molecule also has been chloride, bromide, iodide version has been reported in the literature. So from the literature also, these bonds are slightly longer than the equatorial bonds. Okay, so the important thing is that John Taylor distortion. Why it is happening? Because of unequal filling of the EG orbitals. Because it is copper 9, you have a 9 electrons. So unequal filling leads to a distortion, and this distortion is known as John Taylor distortion. And because of this, axial bonds are slightly longer than the equatorial bond. So out of the 4, your option is all the bonds are equal. This is not correct. Axial bonds are longer than the equatorial one. So this answer B is your correct answer. Okay, so that's all for today. So today I have discussed 2 different problems. One is about the number of metal-metal bond in a complex, and another one is this copper complex where why the bond lengths are different, why the axial and equatorial bond lengths are different, what is the origin of that distortion. So I have explained this is John Taylor distortion. So I hope these questions came in also the same year 2009 GATE. So I hope this will help in understanding the similar question which may come in the exam, and you guys can prepare for the exam. So thank you all for today. So if you guys have any question, you can ask me, you can comment me. Please like, share and subscribe. Thank you guys. Bye bye for today.